This meeting is being recorded.
Provavelmente.
Okay. Well, let's start. People will keep joining us. Hello everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, Linea MCTI. Today, we have the pleasure of having Dr. Ummi Abbas, our researcher at the Istituto Nazionale di Astrofisica, Osservatorio di Torino. Dr. Abbas's research involves the astrophysical applications of astrometry, local cosmology, and experimental relativity, and studies of the large-scale structure of the universe and its evolution. She's also deeply involved in the Gaia collaboration and its data releases. Dr. Abbas, thank you very much for being so kind and having accepted to give us a webinar talk today on such an exciting topic. The floor is yours.
Okay, thank you so much. Can you see my screen and you can hear me fine?
Yes, we can see your screen and your audio is okay.
Okay, great, thank you. Okay, thank you for the nice, very kind introduction. So today I'd like to talk a little bit about the recent bit of research that I've been doing on differential astrometry and using essentially Gaia. So initially with Gaia simulations, and then also I'll talk a little bit about the Gaia data that we are looking at, that we've been looking at recently. And there's a lot of fever going on because we are going to come soon to the DR3 release of Gaia, which is coming up in June. And so here's just a brief outline of my talk. I'd like to give a brief overview on the Gaia space mission and talk about the principles of the differential astrometry. What are the challenges, especially to using global astrometry, because Gaia is optimized for global astrometry, and instead here I'll be focusing mainly on differential astrometry, which is more interesting on small scales. So if you want to look at science cases in small fields and see what kind of information you can get out. Then I'll talk about the systematic effects. Then one of the main things that is necessary for differential astrometry is to obtain a micro-arcsecond stable reference frame. And then I'd like to focus on the Garrick experiment. Okay, so Gaia is essentially a space astrometry mission, and it's carrying out essentially a revolution. And as we can see here on the top left figure, is essentially shown the Gaia scanning law. And I'll come to this in more detail also as I go through the talk. But essentially we can see that it is expected to have about 80 average crossings per star over the 5 years and so on. So this depends on, the cadence, so which area of the sky you look at. And if you're along the nodes, you have higher cadence observations. And instead, if you're away from the nodes, you have kind of low cadence observations. And when I talk about the revolution, here on the right, we can see the different space missions, so astrometric missions. And like, for example, the Hipparcos mission, which was the predecessor, and that had a milliarc second precision. And instead here with Gaia, we are talking down at the end of mission, we are expecting of the order of 10 microarc second precision. And right now, till this day, we are about 2,834 days in science operations. And we have about 200 billion transits observed so far. And the 10 microarc second astrometry is essentially what you would expect the size of your hand as seen from the moon. So that's the kind of precision we are talking about here. And this is very, I mean, such high precision allows you to do very interesting stuff, even relativistic deflection experiments, which is one of the things that I will focus on towards the end of the talk. And also like exoplanet science and orbital solutions from there. And so such high precision astrometry is really very, very useful. Okay, so here I just want to show the scanning precision that we have. And here, the scanning principle, sorry. So here, as I just briefly showed in the previous slide, we have the spinning axis of Gaia that is inclined at 45 degrees with respect to the sun. And essentially, you have a precession on the spin axis that is of the order of 63 days. And there's a basic angle. So the Gaia has two field of view. So as we can see in this animation, essentially there are two windows which you can view as the field of view, so field of view 1 and field of view 2. And this rotates on and over the Gaia spin axis, which is every 6 hours. It does a full rotation. So the spin period is 6 hours. And as we can see here in this animation, these two field of views then scan the full sky as it precesses, and as such you have a full map of the sky, of the celestial sphere. And so you have more, so as the mission goes on, you have the accumulation of more and more observations and more precision as we go through and produce the next catalogs and the next data releases. So I'll just wait for the... Yeah, so this is then, as it opens up, you see the full, the video is a little bit bumpy, so it's not very clear, but at least one gets the idea of how the full celestial sphere is shown at the end of the scanning. So Gaia DR2, which was released in April of 2018, essentially had about 1.7 billion stars. So we had the astrometry, the photometry, and the rate velocity just shown here, different numbers. And with the last Gaia data release, which was known as the early data release 3 in December 2020, we came up to almost 1.8 billion positions. So parallaxes a little less, and then the photometry, two-band photometry, and that the numbers are shown here, more or less just to give an idea. And with DR3, which is coming up in June, we will have much more information. So we'll have also the astrophysical parameters, the orbital solutions, and so on. So that's going to be coming soon. So at least already with the astrometry of EDR3, we were already able to look at, for example, relativistic experiments. So the astrometry is shown here, and the blue lines are essentially EDR3. The red lines instead correspond to what the solid lines are EDR3. So essentially the blue line is what we got from the actual residuals, from the post-fit residuals of the astrometric solution. So the robust errors. And then the DR2 instead is shown as the dashed line. So that is a little bit higher. So we have more precision with EDR3 essentially. So as you can see, it depends on the magnitude of the stars. And for brightness up to, say, 13th magnitude, as you can see in this figure, we have about a little less than 200 microarc second precision. The red lines that you see at the lowest point in the graph is actually the median formal end of mission estimates. So that's what you would ideally expect towards once the towards the nominal mission release. The focal plane of Gaia is just shown here just to give an idea, because I'll be coming back to this again as to how the scanning and how the observations are taken. So here we have essentially the focal plane that consists of the astrometric field, the photometers, and the radial velocity spectrometer. So it's just to show how large this area is. So we have an active area of roughly 0.75 square degrees. And at the beginning, we also have the sky mapper, and so sky mappers DCDs, and then the astrometric field is where we actually obtain all the astrometric observations. Then the photometry comes just in from the blue photometer, the red photometer, and then the radial velocity spectrometer, which gives the radial velocities. So I will be focusing principally on the astrometry that comes from the astrometric field. So the 9 columns, 9 CCD columns that we see here in the astrometric field. So how does one actually move from a star to an image on the focal plane to the astrometry? So if we look at the star in the sky, so it has a certain position and a certain motion. We observe that, and from the satellite, we essentially obtain the proper direction. And we need to be careful to account for the satellite orbit, the aberration, and the light bending as well. So these are all different effects that one has to be careful, so the physical effects. Then we have the spacecraft attitude that determines how the satellite is observing, essentially. And then we are obtaining the field angles, which are this eta and the zeta in the field of view of the telescope. And essentially, the centroid stellar image is what is obtained in the focal plane. And then once you have this centroid stellar image with all the calibrations and taking into account all the attitude and all the other parameters that are shown here, we can then go back and find the best, the astrometric parameters, essentially, that best predict these focal observations. So when we talk about the focal observations, we're essentially talking about the field angles in the focal plane of Gaia. So the eta and the zeta. So when I talk about the field angles, we are interested in the along scan angle and the across scan angle. So the long scan is the one that has the higher precision typically, and that's the one that allows you to talk about high precision astrometry for Gaia. The challenges instead for differential astrometry, because when we talk about all the way that Gaia does the astrometry, here we are doing this all in the global form, global astrometry. So you obtain all the observations, you put them together, and you do an iteration with the source parameters, and you attain iterative solution, and that is global astrometry. Instead, when you look at the small field of stars, so like for example here, I just show like illustrative three stars in the field. You then take observations with Gaia, but Gaia has this particular scanning principle. So for example, here I just show like if Gaia scans on one time, scans, for example, in one direction, the next scan, it will scan in another direction. And so you will obtain different field angles, or you will also obtain different along scan estimates of the position of these stars, along as well as across scan estimates. So when the stars are bright, you get two-dimensional information. So until 13 magnitude, we have two-dimensional information. Instead, for stars that are fainter than 13 magnitude, we have only one-dimensional or along scan precise information. And so what happens, so then in differential astrometry, we try to put in together all this information. So looking at the same field of stars on different scans, we then have different field angles, and these kind of plates have to be, or I should call them frames rather. So these frames of observations, so in this case, for example, we can think of 3 frames of observations. So as Gaia scans, say, from the top right to the left-hand corner, for the first focal plane envisioned here, we have one set of field angles for the stars. And then on the next transit, we have another set of field angles. And on the third transit, we'll have yet another set of field angles. And this is where the cadence comes in. So if we have a field of stars that has high cadence, then you have more and more observations that can be combined. But then it depends how high cadence it is. If it's high cadence over a short period of time or over a long period of time. So if we have many observations over a few days, then that is obviously ideal for like relativistic experiments. And I'll come to this point again. So what are these systematic effects? We have systematic effects that are of the type physical and also instrumental. So the physical effects like are of the type gravitational deflection. That could be either due to the solar system objects, and so in this case we can think of Jupiter as shown here. So we have like the deflection, the monopole deflection due to Jupiter and the quadrupole. So the monopole deflection and quadrupole are actually very relevant close to the limb of Jupiter. So you have to be quite relatively close to have at the level of microarc seconds. And then, of course, there's the sun deflection. So even at the, for example, even at the ecliptic poles, we have deflection of the order of several milliarc seconds. So all this has to be taken into account very carefully. We also have the aberration due to the motion of the observer with respect to the very center of the solar system. And we have to be, that is of the order, that's quite a high effect. It's actually one of the strongest effects that needs to be accounted for. We also have the effect due to along a cross-scan motion of a star. So as the focal plane moves across the field of the stars, you have this motion in the along a cross direction just due to the way Gaia scans the sky. So you have the precession and also mainly due to the precession motion. So you have to take into account this particular along a cross scan motion. And then of course we have the motion of the star itself. And this also gives an order of several tens of microarc seconds. Instrumental effects are instead the ones that come from the CCDs. So you can have like time-dependent instrument model effects. Also the physical geometry of each of these individual CCDs. There are also distortions and aberrations in the optical system. And we also have to worry about the nominal values of all these focal length and basic angles. So this all goes into really the calibration of the field. And as the mission goes on and with the future data releases, and even we have already seen from DR2 to DR3, for example, the calibrations became were much more accurate, let's say. And so this also gives a higher, more precise catalog also. And this also affects a lot the precision that you get on the actual measurement, on the astrometry at the end. So the stability of the reference frame. So one of the things that is important in differential astrometry before you study any kind of physical effect, either due to planets or relativistic effects or even micro lensing and so on, is you have to obtain first a stable reference frame. So you have to have observations of different reference stars. So it's ideal if you have a field that has several reference stars, let's say several tens of reference stars, and you have several observations, so several frames on different transits, and this allows you to build a reference frame. And the importance of stability is essentially that you have to have many observations. So just to give a quick definition on the stability, so it's essentially this RMS scatter on the positions of the object. So if you have several stars, you look at the RMS scatter of all the positions, and then you look at what is the stability as a function of that. And as I said, you have to have, it's obviously ideal if you have many observations. If you just have like 2 observations of each of these reference stars, it doesn't give you a very stable reference frame. Or it could be very stable if you have a lot of reference stars. But if you have an average number, the more times it is seen on many transits, the better it is for the stability of the reference frame. And this is essentially prerequisite when you study different science cases on different time scales, be it of 1 day or even several years. So in this case, just an example of a star field that we looked at when we were looking at the stability of the reference frame. In this case, I just show again the same focal plane that we saw earlier of Gaia, and we just have a sample reference field here, which is actually around the ecliptic pole. And so in this case, we had a high number of stars, bright stars. And in this case, let's say less than 16, we had more than 100 stars around the north ecliptic pole. And what we did is we simulated the ecliptic pole scanning law observations. So in this case, EPSL just means the ecliptic pole scanning law. And we simulated observations of these stars around the ecliptic pole using the Aegis Lab software suite that is available to us. And this essentially simulates the positions seen and the cadence of observations. And we essentially chose this particular field, which is the ecliptic pole, because if we look on the lower right-hand corner, this shows the scanning of the number of transits that were taken by Gaia, that were seen by Gaia over 28 days. And as you can see, if you look at the two poles, so let me see if my cursor works. Yeah, so the poles, so the north ecliptic pole, the point up here, and the south ecliptic pole, these 2 points had essentially high cadence observations. And so over 28 days, we were able to see the same field of stars every 6 hours. So this is what we meant by really high cadence. So every 6 hours, we were getting observations of these stars. And so that means on every transit, every 6 hours, we were having 1 frame of observations. Once we put together all these frames, so in this case, we have to take into account the star's proper motions and parallaxes. So we remove them a priori. And then we have to also account for the pre-rotation onto the Gaia optical axis vector. We also take into account the mnemonic transformation. This allows us to come into a tangent plane. And then there's finally a Taylor series expansion. So this is essentially the principle of the transformation procedure that we follow, the principle of differential astrometry in our method. And once we have all these plates, we typically perform a plate transformation. So you have the different plates or different frames that have to be reported onto one reference plate. And in order to do this, we rely upon a linear transformation, usually linear, and we use a particular astrometric model. For example, this is one example that we used for the ecliptic pole scanning observations of the reference stars in that case. And here we use many, many unknowns. So in this case, for example, eta and zeta are just the field angles. So the field angle in the along scan, which is eta, and in the second case, the second equation, zeta, is the field angle in the across scan, so the AC field angle. And we just have the instrument model, so it's eta ij plus all the calibration and all that it is involved in the second term. And then once you have taken into account all these elements, you perform a linear transformation. So in the last two equations, we have the A, B, and C, which are just our linear plate parameters that we have to estimate. Mu and P and pi are just, mu and pi is just the proper motion and the parallax. And so you just, either you remove them a priori or you can estimate them. So in the case of the ecliptic pole scanning law, for example, we estimated these. So we had a lot more unknowns, and these are at least per star, you have also the proper motion unknowns and parallax unknowns, and then you, in addition to the linear plate parameters. And so once you put together all this information, we estimated using this Gauss fit procedure, which is just this robust least squares estimator that allows you to bring all the frames onto one reference frame. So for the stability, so coming back to the issue that I was discussing just a few minutes ago. So here, in this case, for the ecliptic pole scanning law, we notice that the standard deviation, as shown here, is exactly the one that one would expect from the standard CCD level location estimation errors. So this plot, for example, on the lower right-hand side shows the input errors, the standard CCD level location estimation errors. So the same solid lines that I had shown, the red lines that I had shown at the beginning for the EBR3 astrometry. So this is the estimates, so the ideal estimates, and essentially what we obtained for using this particular method, we were able to see the same dependence in a long scan and a cross scan. So the two curves, so the lower curve is for a long scan, and the upper curve is just for a cross scan precision. So the standard deviation in these two scanning directions. And we just saw that in the case of using a perfect instrument model or less perfect instrument model, in this case, okay, all parameters. So we used also many instrument parameters, and we see that the estimate is more or less the same. We probably need more stars. So in this case, for example, where I look actually at the stability, so the RMS scatter on the positions of all the stars, we can see the stability in the long scan is much more precise. So the red curves, for example, are at the level of microarc second level. Instead, a cross scan with higher errors and all that is a little less precise, depends a little bit on the magnitude, but more or less we are still at the microarc second level, even in the across scan, sorry, the blue curves in this case. So we saw that we can get the microarc second level estimate with even a modest number of stars, so just around 30 to 40 stars, bright stars in this case. So in the case where you have two-dimensional information, so we talk about stars that are brighter than 13th of magnitude. So in this case, we are looking at the G scale, so the Gaia magnitude, which is a little bit different. So it's not a typical magnitude, but it's actually particular tailor-made to the Gaia observation. So in this case, the G magnitude, so I just use the G, capital G symbol. And we see that if we include the geometric instrument model, so where we have a lot more unknowns to estimate as well, we require also, as a function of that, we require many number of stars, a larger number of fainter stars. And so we have to even go down to 14th of magnitude. But this doesn't diminish the accuracy of the reference frame, as we can see in this plot. So the Garrick experiment. So one of the main things that the differential astrometric analysis was envisioned for is this Garrick experiment. So this is particularly interesting because it's a relativistic deflection experiment around Jupiter. So I'll just quickly touch upon the possible science cases that one can look at with differential astrometry. So I just briefly mentioned this, but we could study many different cases over different time scales, so various science cases. Those over one day, which would be the case of relativistic deflection of light experiments, and I'll come to this shortly. Those cases over a few months, so like, for example, microlensing events, or even experiments over several years. So like, for example, the detection of extrasolar planets and orbital solutions that it entails. I will mainly focus on this one-day experiment, or I would say more like a couple of days, this Garrick experiment. And what is Garrick? So Garrick is just this Gaia relativistic experiment on Jupiter's quadrupole. So the light, as it comes close to a massive object, has a deflection effect due to the fabric of space-time. So in this case, for example, the famous experiments in the past have been the Eddington light deflection experiment. So 1919, when we had the famous sun deflection experiment carried out by Eddington and also Crommelin, they essentially verified Einstein's theory, and they saw this deflection of roughly 1.75, which all of us know quite well. Now, in astrometry, the effect this plays a strong effect, and we have to take this into account in all sorts of modeling. And we have to be very careful, because in order to have the high precision as a microsecond astrometric precision of Gaia, we need to take into account all these effects, and we have to be very careful, especially for this relativistic light deflection. And so that due to the sun and the planets, and for example, in the case of the sun, it is of the order of 4 milliarc seconds perpendicular to the Earth-Sun direction. So you do notice, like for example, at the ecliptic pole, when we took the ecliptic pole scanning law experiment, we have to be careful to account for, if you were to use actual observations by Gaia, you would have to account for a 4 milliarc second effect even there. And this is generally accounted for in modern astrometric space missions. So that even the milliarc second precision that was carried out by Hipparchus, and now even at the microarc second precision that is being carried out by Gaia. So we always have to take into account these precise deflection effects. For example, in the solar system, this table shows the different deflection effects due to different solar system bodies, that due to the monopole and that due to the quadrupole. The quadrupole is essentially expected from bodies that are sort of oblate. So the ones that are purely spherical have only the monopole effect, deflection effect. Instead, Jupiter, Saturn, Uranus, and Neptune, which are slightly oblate, have also this quadrupole deflection, so a higher order term in the deflection, relativistic deflection effect. And for example, that due to the sun, for grazing ray is, as we just saw in the previous figures, is shown here, so 17,000 milliarc seconds. Close to Jupiter, which is the one that we are really interested in. So in this case, we just look at the line of Jupiter. We see that the grazing monopole deflection is of the order of 16 milliarc seconds. 90 degrees from Jupiter, it is still of the order of 1 microarc seconds if you take observations that are 90 degrees away from Jupiter. Instead, the quadrupole deflection effect is of the order of 240 microarc seconds. So this is grazing. Now, the monopole effect falls off as 1 over b. So if you look at the impact parameter, it falls off as the inverse of this impact parameter. So the monopole effect is much longer lasting at the milliarc second level. So for example, if we are able to take observations close to Jupiter over several days, we could still see a milliarc second deflection close to Jupiter as Jupiter moves across the sky. So as Jupiter moves close to the star, you would have a higher deflection effect, and as it moves farther away, you would have only deflection effects that decrease as 1 over the impact parameter. And in the case of the quadrupole effect, instead, is much more challenging, because the quadrupole effect is not only much more smaller, so it's only of the order of, in this case, 240 microarc seconds. It is also embedded within the larger 16 milliarc seconds signal of the monopole. So it has to be disentangled from that. And not only the quadrupole effect falls off as the 1 over b cubed. So the inverse cube of the impact parameter. So if the star, so this effect is very short-lived. It's essentially, you would see it there at the level of above a few hundred, at the level of 100 microarc second for just an hour, say, and then it's already gone, the way Gaia scans across the sky. So it's a very challenging effect. So actually the Garrick experiment, which is an experiment on the quadrupole, is meant to detect for the first time this particular signal, so the 240 microarc second signal from this table. So that's what I just mentioned, and it would be a first-time deflection in the optical, so it's highly important from that point of view. The first deflection that has been obtained has only been in the past, close to Jupiter, has only been in the radio, so from the VLBI measurements. So in the radio measurements of there, they looked much further away and they obtained a signal that was of the order of a few hundreds of microarc seconds. So in this case, we are talking of obtaining a signal that is of the level of several mass, milliarc seconds. And instead, at the end of the nominal mission, we would be able to, so even at the 20 microarc second level, we would be able to measure the Jupiter, the deflection signal due to Jupiter's quadrupole, which is the much more challenging one. So once you disentangle that, then also it's very short-lived, so you would have to measure it exactly when the star is closest possible to the limb of Jupiter. So in this case, it is very challenging. So as I showed even before, we have always a scanning of Gaia across the field of stars. In this case, there's also Jupiter in the field of stars. So we have to put together all these frames of observations. So we observe, and the more number of frames we have on each and every transit, the better it is. Ideally, in this case for Gaia, there was a particular event that was targeted by Gaia. So it was an event that was observed in February of 2017 and that we are actually processing right now. And those observations were ideal because Gaia was optimized to take high cadence observations in that particular field. Because except for the ecliptic pole scanning law and the nodes, you don't really get high cadence observations. So in the case of this particular, we were targeting this experiment, so observations close to Jupiter. And in this case, we really went to optimize the scanning law. And so we had to carry out a targeted campaign, optimization of the scanning law of Gaia, in order to get such high cadence observations. And those scanning law parameters are actually what was used by Gaia to obtain the optimal event that was observed in February 2017. So instead here I show a simulated star field of what can be expected. And we see, for example, on different transits, so if I just go back here, so different transits, so as the focal plane moves across the field of stars and Jupiter, it doesn't observe Jupiter directly, but it observes the stars surrounding Jupiter. And on these different transits, we have the different, what do you call them, field angles, so eta and zeta coordinates. So in this case here, for example, I show eta and zeta coordinates observed by simulated observations by Gaia around the field of, so Garrick field, so this particular event in 2017, so I simulated this effect. And if we look closely here, we see okay, so the target will be shown in the next slides, but essentially there's Jupiter, which is the red dot, which is moving across the field of stars. And these different stars are seen, so they could fall into view and out of view, and you see them moving slightly. So this is a simulation on loop. So 15 transits that are shown on loop. So you see Jupiter on each of these 15 transits. So it moves slowly up the field, close to the target star, which is just in the center, is the one that is closest to the red Jupiter position. And all the other reference stars that are seen and sometimes are not seen, sometimes are seen, because this depends on how Gaia scans across the field of view. Sometimes it is too close. So if the star is too close to the edge of the field of view, it is not seen. Ideally, it has to be in the middle to be seen. So that's why sometimes stars fall in, sometimes they fall out, in and out of this, this picture. So this is a challenge, actually. So we have to be able to put together all these kinds of observations. And this is why I said that it's ideal to have a large number of reference stars seen on many transits. Otherwise, it's difficult to set up a stable reference frame, and especially down to the microarc second level. And so in this case, we have, we can see a bright set of stars down to the 13th magnitude. 13th magnitude, why? Because at that, up to the 13th magnitude, we know we have two-dimensional information. So the eta and the zeta coordinates. So the along scan and the across scan information. And if I were to simulate on top of the same field of stars, I simulate the effect of the monopole deflection. Here we can see how the monopole deflection takes place. So this is obviously enlarged because we are looking at on a field of view that is of the order of a degree. And the effect of monopole deflection grazing to the limb of Jupiter is only 16 milliarc seconds. So I had to enlarge this by almost a factor of 50,000. And so this shows up in this way. So at least one gets an idea how the target star, which is the big yellow point that falls closest to the red Jupiter position, how that actually, what kind of deflection it undergoes when it sees the monopole deflection due to Jupiter. So it looks like it's a kind of like a bow, you would say. So it's quite interesting. Instead, the quadrupole deflection is much more short-lived, so you would only see it on a couple of transits. So for example, in this case, we just see it on 2 to 3 transits, and the yellow dot really just has a very quick effect. So there's one loop going down, moving downwards from the red Jupiter position. So the red dot that moves upwards, so Jupiter is just moving across the field. And this quadrupole deflection effect that is multiplied by yet another factor of 70. So in this case, the total magnification is 70 times 50,000, because otherwise the effect is only at the level of tens of microarc seconds. So highest is 100 microarc second in this case, how close it falls to the position of Jupiter. So this is also an interesting effect. So what you would see is actually the total deflection effect due to the monopole and the quadrupole. So what one observes is the sum of these two effects. And so this is what I meant by saying that we have to be able to disentangle the quadrupole deflection effect. The simulated signal looks like this. So in this case, in this figure, I just showed an example of the monopole deflection signal in the along scan and the across scan. So the upper two panels, on the left side, we see the along scan monopole deflection. On the upper right hand, we see the across scan Jupiter monopole deflection. And we can just see what kind of effect it has. So for example, for the target star, so the target star is the one that is closest to Jupiter. So in the case of the simulations, what I showed here, it is the big yellow dot, the big yellow filled diamond is the target star. So the target star is the one that was observed closest to the limb of Jupiter. And this particular target star, on different transits, so in the case I was showing like 15 transits, high cadence close to Jupiter, this is how the deflection effect would look like. I'd like to just point out in the top left-hand corner, if we just focus our attention there, so the along scan Jupiter monopole deflection effect, essentially you would see an effect that increases. So the closest transit closest to Jupiter was the fourth transit. So here I show the simulated effect, but we are actually looking into the data, and this is also what we see in the data from the processing of the data. And so the one closest to the transit, we see a deflection signal that is of the order of 10 milliarc seconds. And essentially, if we were to observe the position of the target star and reduce it using differential astrometry and all the methodology and the framework I had shown before, we would expect something very close along the how would I say, the asterisks. So we would expect a distribution of points close to the asterisks. And this is what we are looking at the moment. So instead, the lower two panels is what one would expect for the quadrupole deflection signal. The range is much smaller. So in the upper panels, we were looking at the milliarc second range. So the signal is, if one remembers, is 60 milliarc second grazing limb. Instead, for the target star observed closest to the limb of Jupiter, it's of the order of 10 milliarc seconds, which was already quite close. So it was already observed very successfully. And I'll show an example just shortly. The quadrupole deflection effect, which is shown in the lower two panels, is much more smaller. So that's only of the order of at the microarc second level. And hence it is much more challenging. And as, for example, shown here, we would have to have, in the along scan, we would have to have a precision that is definitely 10 microarc seconds, for example. Otherwise, we wouldn't even be able to disentangle and a long scan quadrupole deflection signal as shown here. If we have it of the order of several tens of microarc-second, then one can still do it. It depends on how what is the scanning angle and all that, how Gaia scans across the field of stars. So this is just a simulated example. So the actual observation that was taken by Gaia of this agaric event, so the previous slide I showed you only what is simulated and what is expected and what one can see and what one can obtain with the differential astrometric framework. Instead, this is an actual observation of the agaric event. So the Gaia satellite was optimized with the 2 free scanning law parameters, and this is essentially an actual observation of Jupiter seen in the field of view. And for example, here we can see the Jupiter, which is not actually observed. So it's essentially this hole in the figure here is Jupiter. So it's removed from the observations because it's too bright. Otherwise it would burn the CCDs. And we see the target star. So the one that I was simulating in the previous simulation, so the big yellow diamond. In this case, the target star was observed at this particular, just barely 70 arc-seconds from Jupiter's limb. And this observation was taken towards the end of February in 2017 and is a very successful observation. So it's not the closest observation. It was the 3rd closest, I think, or the 3rd or the 4th closest. And so this is an example of how the actual observation is seen on the focal plane. And in fact, you can even see the gap between the 6th and the 7th CCD rows. So if you remember the focal plane of Gaia, we have the 9 CCD rows in the astrometric field. And so in this case, for example, in this image, we can see the gap between the 6th and the 7th row. So the one that is shown so here, this gap over here, and we have the target star that is seen in 1 CCD row and the 1 CCD column, sorry, and this Jupiter is seen in yet another CCD column. So it was seen between the 6th and the 7th. So this is a very interesting observation, actually taken by Gaia. So as a summary, and this comes towards the end of my talk, so differential astrometry, so I just abbreviated to say DA. So this differential astrometry can be used to establish a microarc-second stable reference frame. And also it can be used to study science cases over different time scales. So over 1 day, over a month, or even several years, most likely a year, because it depends on the cadence and so on. The astrometric modeling would have to account very carefully for the physical effects, and these could be due to the aberration, the along and cross-scan motion, and the proper motions of the stars, as well as the instrumental calibrations. So the calibrations are particularly important, and especially the AGES solution that comes and the astrometry that we use is highly dependent on the calibrations at the end of the day. So that's why with EDR3, we were able to look at the deflection of light experimental with Gaia, and but with DR2 already the calibrations were not as accurate, and so we didn't get as precise deflection signal. We looked at the high cadence ecliptic pole scanning law observations, and we saw how that allowed us to construct a small field differential reference frame, and in that case over short time scales. So in this case, my whole talk was only focused over short time scales. So I was only looking at just a few days of experiment, either simulated or even the Gaia experiment. The Gaia scanning law, the optimization led to, it was optimized for the Gaia experiment, sorry, and this has led to observations that have been highly favorable. So on the previous slide, I showed one example of a very nice observation close to the limb of Jupiter, and this is being currently studied within the Gaia consortium. In fact, I'm part of the team. We are submitting results soon, so unfortunately I couldn't show any plot here, but it is similar to the one of the simulated effect of the target star close to the limb of Jupiter. So it's very promising, and this is a very exciting time for us. And also we are coming close to the DR3 release in June of this year. So there'll be an avalanche of papers coming out. So we'll see a lot of interesting results soon to come up. Thank you for your attention. I can take any questions.
Well, thank you very much, Dr. Abbas, for the very interesting talk. And, we now have time for some questions from the audience. If you joined us on YouTube, please put your question in the comment section. And if you join us on Zoom, please raise your hand. Julio, go ahead.
Hello, can you hear me?
Yes, I can hear you.
Okay, so I'm speaking very close to the microphone. Okay, thanks for the excellent presentation. When you showed some pictures to illustrate the effect of the deflection by Jupiter on stars, but my question is. Is it possible that also the inner satellites may influence in the position of the star? I mean, Jupiter is crossing is going close to the star, and the inner satellites they will also be there. So, how important is this? I know that the deflection by the smaller satellites is not large, but do you consider that in your model? And would that model perhaps be available to the public?
Yeah, okay. Yeah, this is a very important point. In fact, it's a nice and good question also. So so in fact, one of the satellites, one of the observations, one of the transits was even blacked out due to one of the satellite being too close to the target star. So that was removed, but that's a different story. So coming back to the deflection effect. So the deflection effect is rather small. Already for a grazing limb, grazing starlight close to Jupiter, it is milliarc seconds. So that due to the satellite is much smaller. However, yes, at the microarc, so at the microarc second level, it is not, at least, okay, so for the astrometry that we have now, for the EDR3 astrometry, it is not so important. However, I think even at the microarc second level, the 10 microarc second astrometry level, it is not so crucial. So it would be an effect that I think is much smaller, is only of the level of microarc second or so. However, coming back to the issue of the modeling takes into account all these very high precision effects. So in fact, it is the observations are really very highly precise. So the Gram model that is inside the Gaia model is the Gaia relativistic model, which is actually taken care of by Kliuner, Sergei Kliuner, and he has been very careful to account for all the effects from all other objects within the solar system, especially the planets and the Galilean moons and all that, possibly as well, but definitely the planets, because that has that's where one has to be at the microarc second level. One has to be careful.
Okay, thanks a lot.
Thank you, Julie. More questions? Altair, go ahead.
Yeah, just complementary to Julie's questions. You talk about Jupiter deflection, but not about the sun. Would the sun also affect because even at opposite direction of the sun is a very large deflection. So it would contribute as well.
Yeah. So
it's not clear to me. It's not clear to me that both effects are just the summation of the deflection of the sun and the Jupiter. It's not intuitive for me.
Yeah, so it is. It is the sum, and in fact, it's just removed. So in the plots that so those are simulated effects, but in the actual data we also see, and it's a cumulative effect. So we remove it from the signal. So it's even at the level, it's still at this level for the milliarc second level, we still have a signal even due to the sun, and it's just removed. It's a summation. I hope that answers your question, or do you have another question? Or
No, that's it. Thank you.
okay.
Thanks, Ate, for questions. Well, while we wait, I have a question. You talked about targeting campaigns. How does it work? Is it possible to apply for targeting campaigns with Gaia?
Sorry, I didn't get your question. I talked about the
Targeting campaigns. I don't.
Okay.
Maybe I misunderstood. Are there targeting campaigns with Gaia observations? Like if you want to propose something.
Okay. Like so no, technically Gaia in the case of optimization, so I guess you're referring to the optimization of the scanning law for the Gaia experiment.
Okay.
Yeah. So in this case, it was only done specifically for the Garrick experiment. So no, because Gaia is not like, it's not like HST, which is a pointing satellite. Gaia does its own scanning.
Sure.
So what happens is it's even for the Garrick experiment, we had to tell the mission controls, so the mock had to be told months ahead, even a year ahead, what were the initial scanning law parameters in order to target this particular experiment. So now it is frozen. I mean, the scanning law parameters are only changed in very exceptional cases and not for at this point, not even for science cases. If the scanning law parameters undergo changes, it's because of other reasons due to the satellite or the way they want to optimize the scanning scheme due to other reasons, the instrument and so on. Garrick was the only targeted observations that were carried out by Gaia, because this was something that they had in mind even at the beginning of the Gaia commissioning phase and during the conception of the experiment. So this is quite, goes back quite a bit. And so technically, no. So the only thing that is released to public, so even the observations that I use for the Garrick experiment, so the ones that I've shown you, and especially the field angles that come out, the ones that we have used, are not released to the public. So the epoch information in this release is not going to be given to the public. So this is actually a test that we have done within the consortium, and the public will only receive the catalog. So only what is given in the DR3 release that will come in June, or what was given in EDR3, so the astrometry and the two-band photometry. That was the only thing that is given to the public. So for example, the Garrick experiment, if it wants to be verified by someone outside the consortium, is going to be a little bit tricky at this point. But they are talking about releasing epoch information, all the epoch information in the DR4, which would be, for now they're talking about 2025, but it could get later than that. But yeah, more or less 2025 onwards, we can get so for example, what one knows as a time series for the photometry and the epoch information that would come out in future data releases and not with DR3, unfortunately.
Well, that will be my second question. Thanks.
Yeah.
About if epoch information will be released.
Yeah,
okay,
that would be DR4. So they are talking now in the consortium which products to release, but the idea is to release the epoch information in DR4. So not the next one, DR3, but the following one.
Sure. Well, thanks. If there are no questions, I will ask a last question. When you were presenting the transformations to the field, did the transformation is done before you apply the fitting of the parameters using Gauss fit, or is it part of the Gauss fit procedure?
Yeah. So the transformation I do before. So, like for example, the a priori removal of the proper motion and the parallaxes, and the transformation due to the Taylor series expansion, and so on, that is done before the linear plate transformation. So the linear plate transformation is what is taken care of by Gauss fit.
Okay, thanks.
Yeah. So the Gauss fit essentially does the last step. So it does the ABC. So it estimates the plate parameters, which are the A, B, C, D, E, F, essentially. So the linear plate parameters.
Okay, thank you. Are any last questions? Okay, let me see here. No. Well, if there are no more questions, we will now wrap this up. And there is a comment from Felipe. Very interesting work. Congratulations and thank you. Okay.
Thanks, you.
This presentation will be available on our website and on Linus YouTube channel. Thank you everyone for attending, and a special thanks to Dr. Ummi Abbas. Thank you very much. Everyone, have a great day. Stay safe, and I hope to see you all again on our next webinar. Thank you. Thank you very much.
Thank you.
Thank you, people. Bye.